In the last video, I introduced the concept of effective nuclear charge, where we were calculating the Z effective. And in that video, we were using the simple way of doing it, which was that our Z effective was going to be equal to our Z, which is just our atomic number, minus the shielding electrons. Okay, so the number of inner core electrons. Well, I ended off the last video saying that it really wasn't quite that simple. And unfortunately, the explanation for this is pretty complicated, and it involves using some pretty advanced calculus. So I'm just going to run through the very basic idea, as basic as it can be, while still giving you a good picture of why this happens. So before we were looking at it, we said, okay, here's our positive nucleus. Say we have these inner core electrons. Well, let's say I have an element that has, let's see, 1s2, 2s2, 2p, say 4. Okay, this means that we'll take away some of these. This means that we're going to have 6 valence electrons. Okay, because this is going to be our outermost layer. That means this is going to be our inner core electrons. So we only have 2 there. So I'm going to have 1, 2, 3, 4, 5, 6. Okay, and of course it doesn't really look like this. But what this is saying is that we have 6 electrons on the outside, and that we only have 2 electrons that are shielding. So we have our Z effective. We say our Z is going to be 8 minus, and then we only have 2 that are shielding. So we're going to have a plus 6 Z effective charge. Of course, this is oxygen, and as it turns out, it's not quite this easy. So let's take a look at why. All right, get up there. Okay, we learned that our orbitals can be defined using Schrödinger's wave function equation. Okay, so the wave squared is just going to be basically the probability of where an electron is most likely to be found. And we said that we have shells, which are our N. Okay, so these are our shells. And then we have our L's, which are our subshells. So for example, if we have 2s, we say that n is equal to 2, and then our subshell is going to be this s orbital. So remember, L is equal to 0 for s. So it was s is 0, p is 1, d is 2, f is 3. Okay, for our value of L. And after they did a bunch of calculations, what they did is they graphed them out on what we call what we call a radial probability function curve. And it basically just tells us, okay, the distance from the nucleus and the probability of finding an electron there. So here's what we found. When we were dealing with the 1s subshell, here we have our n is equal to 1 and our L is equal to 0. We found this. Here we have our distance from the nucleus, and this is going to be in angstroms, which are very, very small. We're going to put 0 here. I'm going to put 1 here and 2 here. Okay, and over on this side we have our probability. And of course this is when n is equal to 1 and L is equal to 0. And what they found is basically this. That the max value was just slightly under 1 angstroms. So what this tells us is that the highest probability of finding an electron is going to be just under 1 angstrom from the nucleus. So what we say is that the electrons in the 1s orbital are going to be very, very close to the nucleus. Okay, very, very close. So that's for the 1s orbital. Now if we move it up, when we do the 2s orbital, this is when n equals 2, and then again L is equal to 0. We're going to have the same axes, but this time I'm going to distribute them just a little bit differently. We have our 0, 1, 2, and 3. Again, this is our probability at 2 and 0. Okay. What they found was kind of surprising, and again, the results are based on this mathematical equation that later they then confirmed with actual lab data. But what they found is that it kind of looks like this. It's going to approach 0 right here, and that we're going to call a radial node. Okay, that says node with an N. Okay, that's called a radial node. That's why we're going to call this a radial probability chart here. And what we get is we get these two maximum points. We call this the inner max point, and then this is just our regular probability maximum. So what this means is that we have a maximum point that's really close to the nucleus right here, and then we have one that's a little bit further out, which means that in a 2s orbital, electrons are going to spend some time pretty close to the nucleus. And what we've learned in the past, and what we've done when we've done our simple z-effective charge, is we've treated the 2s and the 2p orbitals as being equal distance from the nucleus to one another. But that's actually not what we see. I'm going to move this up just a little bit. What we see is that when we do, let's do back here, when we do the 2p orbital, when n equals 2, L equals 1, we see something a little bit different. We have our 0, 1, 2, 3 again, but we just get this. Okay, so our max point is pretty similar between our 2s and our 2p. The difference is that there is no inner max point. Okay, there's no radial nodes. Our line here does not approach 0 the way that it did when we were dealing with the 2s orbital. So what this means is that in the 2s orbital, electrons are spending more time closer to the nucleus. Okay, because remember on our x-axis here, we're dealing with distance from the nucleus, assuming that at 0 angstroms here, we're at the nucleus. So this is why then we have to use kind of a little bit more of a complicated equation when we're calculating z-effective, but that really shouldn't be something that you're dealing too much with. You mostly need to know the concept behind it. And let me just show you one more thing. If you've noticed, there's an actual trend here, and you'll learn this in higher level chemistry courses that I know that you're all going to take. But we say that there's a pattern. So we have a radial node pattern or equation. We say that it's, so the number of nodes, and remember the nodes is when we approach 0, right here. This would be the node spot. So the number of nodes is going to be equal to whatever the value of n minus the value of L minus 1. And we can see that if we go back and you take a look at the notes that you've written down from this, is we can actually predict the number of nodes. So when we have, let's say we want to go a little bit further, we can say, okay, the 3s orbital should have n equals 3 minus 0, because L equals 0, so 3 minus 0 minus 1. So we can predict that it's going to have 2 nodes, and it does. It kind of looks like this. Okay, and then if we have the 3 p's, we can say n equals 3. P is 1, so that's 3 minus 1 minus 1. So we can predict that it's just going to have the 1 node. And then 3D, we could say n equals 3 minus 2, because D is 2, minus 1, which you should automatically be thinking, okay, that equals 0, so we should have 0 nodes. So it's a pattern that we can kind of see over and over again, and this again is based off of the Schrodinger's equation of where an electron is most likely to be found. Where's the highest probability of finding that electron? Hopefully this makes your reading a little bit easier when you're looking at the graphs that are shown in section 7.2. There's an assignment associated with these videos that you will find on Edmodo.